Hello and welcome to Lesson 25, an introduction to speculative side-channel attacks. So back in Lesson 4, we were first introduced to the concept of speculation, which is where the CPU performs work that may not have been explicitly requested by software and which may not even be required. One of the examples we stepped through back in Lesson 4 was this one here, where we are calculating the average age of an array of people. To do this, we first loop through each person in the people array, summing up each of their ages, and we then divide that sum by the number of people in the array. Now, if we were to consider what this loop looks like from the perspective of the CPU, well, on the very first iteration of the loop, we're asking the CPU to load these 4 bytes here, which we as the software engineers writing this loop know corresponds to the first person's age. On the second iteration of the loop, the CPU is asked to load these 4 bytes here, which we know corresponds to the second person's age, and then for the third person's age, and so on. And it's not going to take long for the CPU to notice the pattern here. Load 4 bytes, skip 12 bytes. Load 4 bytes, skip 12 bytes. And once the CPU does notice a pattern like this, then it may begin to speculate that we're going to continue asking it to load 4 bytes, skip 12 bytes, load 4 bytes, skip 12 bytes. And as a result of that speculation, the CPU may begin to fetch these 4 bytes here ahead of time, before being explicitly asked to do so by software. That is to say, before we've actually gotten as far as the corresponding load instruction in software. Now, if it turns out that we speculated wrong, and there were actually only, say, 3 people in the array, and we did not need to load these 4 bytes, well, that's fine. The CPU will simply discard the loaded data. But if we speculated correctly, then we may have just saved ourselves some time by already beginning the process of loading that data into the CPU before being explicitly asked to do so. And as we saw, this kind of preloading of data based on pattern matching and heuristics is just one form of speculation. Other forms of speculation include speculatively fetching instructions from addresses that the CPU thinks we may soon branch to, speculatively walking the page tables to translate virtual addresses that the CPU thinks we may soon need to access, and even speculatively executing instructions past the current program counter in an attempt to keep the CPU pipeline as well utilized as possible, including speculating as to whether or not a conditional branch is taken before we actually know the result of evaluating that conditional branch. And indeed, this last point here is the very reason we need not 1 but 2 DMBs in our message passing scenario. That is a DMB on both P0 and P1. So despite P1's read of the mailbox being predicated on the result of the conditional branch on line 9, the CPU is able to speculatively execute past this conditional branch and perform its read of the mailbox ahead of time, before actually knowing whether the flag is set. And by placing a DMB in between P1's 2 reads, we ensure that its read of the mailbox is observed after its read of the flag that sees the flag is set. Now, there are some very good reasons as to why the ARM architecture permits this kind of speculation. And simply put, it's one of the fundamental driving forces behind the high-performance profiles of modern-day CPUs. If your CPU did not perform any kind of speculation at all, well, kiss goodbye to your performance. And besides, this kind of speculation is completely safe, right? After all, if we speculate wrong and the CPU loaded something that it should not have loaded, then we'll simply discard that loaded data from the CPU's microarchitectural state without ever committing that loaded data to the CPU's macroarchitectural state. Put another way, the software running on the CPU never has visibility of any data that was loaded under misspeculation, so we're fine. Or at least, so we all thought. And then along came Spectre and Meltdown. So what are Spectre and Meltdown? They are a range of catastrophic security vulnerabilities exploiting the effects of speculation, and which were first publicly disclosed back in January 2018. Why were they deemed catastrophic? Because they affected nearly every relatively modern CPU in existence, regardless of architecture and vendor. Intel? Yes. AMD? Yes. IBM Power? Yes. ARM? Yes. When it comes to hardware vulnerabilities, they're usually confined to a single CPU core design or to a single chip. In certain rare circumstances, you may see a family of chips affected by a particular vulnerability, and rarer still, there may be architecture-level vulnerabilities affecting, say, all x86 CPUs or all ARM-based CPUs. But Spectre and Meltdown were industry-wide. Everyone was affected in some way by at least one of the several variants that ended up being published. So this led to a significant industry-wide perspective shift with regards to the effects of speculation, and in particular, with regards to the security implications of speculation. They also came with their own little logos that you see here, and I particularly like the Spectre one on the left because, as we'll soon see, speculative side-channel attacks typically involve the CPU speculating past a conditional branch and the attacker then recovering secret data by measuring the ghostly imprints left on microarchitectural state by that speculative execution. So a ghost wielding a branch that it wants to hit us over the head with is incredibly apt. Okay, so what are we actually going to be talking about on this topic? Well, we've split this up into 2 lessons. This first lesson will serve as a general introduction to cache timing side channels, and we'll take a look at how Spectre Variant 3 works, also known as Meltdown. Now granted, Meltdown does not actually require any barriers to mitigate it against it, so there's an argument to be made there's no need for us to cover it on this course. However, I actually find Meltdown to be the best introduction to how speculative side-channel attacks work. And as we'll soon see, in many ways you can think of the other Spectre variants as being more advanced evolutions of the same thing. So that's what we'll be covering in this lesson. And then in the next lesson, we'll build on our new understanding by taking a look at Spectre variants 1 and 4, as well as straight-line speculation. And as you can see at the bottom of the slide, we have a whole bunch of barrier instructions relating to speculation. We've got the CSDB, SSBB, PSSBB, and SB. So we'll see what those barriers are and how we can use them to defend against speculative side-channel attacks. As a brief aside, regarding the -US, -PHT-SAIP, and -STL suffixes that you see on these Spectre and Meltdown variants, speculative side-channel attacks got a lot of attention in the wake of the initial Spectre and Meltdown disclosures, and a whole bunch of other attacks, variants, and sub-variants were popping up almost every month. And the thing is, the security researchers publishing their papers were all looking for their own catchy names and logos. Quite understandably as well, given the mass media appeal of names like Spectre and Meltdown and those fancy logos we saw on the previous slide. And so we had all these new variants popping up with names like LazyFP, SGX Spectre, Foreshadow, Smother Spectre, and plus a whole bunch of numerical identifiers like Variant 1.2 and Variant 3A. And it just basically became really hard to firstly track all of these different variants and also to remember which variant was which. So some of the security researchers involved in the initial Spectre and Meltdown disclosures have attempted to formalize and standardize the naming conventions, and that's what you're seeing here. So the US in Meltdown US is short for User Supervisor, and it's just one of about 14 different possible Meltdown variants that have been identified as of May 2019. Similarly, PHT-SAIP is short for Pattern History Table, Same Address Space, In-Place Branch Predictor Training, while STL is short for Store to Load. These make up just 2 of around 13 different Spectre variants that had been identified by the same time. Now, there's obviously no way for us to cover more than 27 different attacks, variants, and subvariants in these 2 short lessons. Plus, just to reiterate, these 2 lessons only aim to serve as a brief general introduction to this topic, so further reading is strongly recommended if you're actually going to need to defend against these kinds of attacks in your own work. And indeed, if you scroll down on the page, I've put a whole bunch of links down below the video to various resources that you may find useful. This includes things like the original Spectre and Meltdown white papers published by the security researchers that discovered them, and also their attempts to formalize and standardize the naming conventions with the Meltdown US and stuff like that. We've also got a link to ARM's official white paper that it published in response to Spectre and Meltdown, and finally, ARM's official white paper that it published in response to straight-line speculation. Fun fact, I actually co-authored that last one, covering straight-line speculation, while I was a member of ARM's security response team. So I might be slightly biased, but you should totally check that one out, yeah? All right then, let's make a start. And I first want you to consider this simple readB function. It takes a pointer to some byte in memory, dereferences the pointer, and returns the loaded value. Super simple. Now, what I want to convince you of is that this second function, infer_b, achieves exactly the same thing, albeit in a rather roundabout way. That is to say, infer_b is able to, well, infer the value of the byte in memory through what we call a cache timing analysis side channel. So how does that work? Well, we're first allocating an array of bytes that is 256 cache lines in size. On most ARM64-based systems, a single cache line will be 16 words wide, so 64 bytes wide, and that's what we're trying to show with this diagram at the bottom of the screen. So the first row represents the first cache line's worth of bytes in memory, with each square being a 4-byte word, and the second row then represents the second cache line's worth of bytes, the third row represents the third cache line's worth of bytes, and so on. Now, on the next line of code, we flush everything in the data caches out to DRAM, so as to ensure that none of that array that we just allocated is present in the cache. And that's important because on the next line, we're performing a load of a word from a specific cache line in our array, where the index of that cache line is determined by the value of the byte in memory that we are trying to infer. The intention being, this load will generate an allocation into the cache for that cache line. So for example, if the value of the byte in memory is 2, then we're going to be trying to load the first word of the cache line at index 2 from our array, which is this red square here. And that load is going to pull that entire second cache line into the cache. So all of these red squares here will now be in the cache. Crucially, thanks to our earlier call to flush caches here, none of the other cache lines in our array will be present in the cache at this point. Only the cache line whose index matches the value of the byte in memory that we are trying to infer. With that in mind, all we need to do now is loop through our array of cache lines using a high-resolution timer to check how long it takes to access each cache line. The idea being that the cache line we just pulled into the cache with our read on line 7 will complete much quicker than all of our other reads of the other cache lines. Ergo, the index of the cache line that is quickest to access in our array is the value of the byte in memory that we are trying to infer. And just to really drive this point home, if the value of the byte in memory is, say, 0, then the read on line 7 will pull the cache line at index 0 of the array into the cache, and we'll be able to infer the value of the byte as being 0 because the cache line at index 0 of the array will be the quickest one to access. Similarly, if the value of the byte in memory was instead, say, 255, then the read on line 7 will pull the cache line at index 255 of the array into the cache, and will then be able to infer the value of the byte as being 255 because the cache line at index 255 will be the quickest one to access. Pretty cool, right? Now, there are some things to keep in mind here. Firstly, if we were to take a closer look at the code that determines which cache line in the array is the quickest one to access, it's probably going to look something like this. So here we're looping through each cache line in the array, and we're then using a high-resolution timer to measure how many nanoseconds it takes to access that particular cache line. We're then comparing that time against the current best time, and if this cache line was the quicker one to access, this cache line becomes the new benchmark. And finally, once we've iterated through each cache line in the array, we can simply return the index of whichever cache line was the quickest one to access. Now, can you spot any potential issues with this approach here? Well, we literally started off this lesson talking about this average age example, where the CPU may notice the pattern of us loading 4 bytes, skipping 12 bytes, loading 4 bytes, skipping 12 bytes. And so the CPU may begin to speculatively prefetch bytes ahead of time based on that pattern matching and heuristics. Well, the exact same logic applies here, right? Here we're loading 4 bytes, skipping 60 bytes, loading 4 bytes, skipping 60 bytes, and the CPU may notice this pattern and begin speculatively prefetching other cache lines from our array into the data cache ahead of time, which would be bad for us because we're relying on there only being a single cache line from our array present in the data cache at the time of us performing these accesses. With that in mind, a more robust solution will need some way of suppressing this kind of speculative prefetching from being performed by the CPU. And typically what we'll do is space apart the cache lines by some relatively large number of bytes in our probe array. So for example, we may space the cache lines apart by at least one full page of memory. So 4K, 16K, or 64K, depending on your particular hardware platform and your operating system. That's usually enough to prevent the CPU prefetcher from kicking in, as the locations will be deemed to be too far apart spatially. We can also iterate through the probe array in a random fashion, rather than iterating through it linearly, to make it harder for the prefetcher to notice any patterns in our accesses. That said, we've got to keep in mind that a region of normal memory may be speculatively fetched at any time for any, or indeed no, reason. And so the second thing to be aware of is that there may still be some level of noise caused by this kind of prefetching. And in that case, we'll need some other way of improving the signal-to-noise ratio. That's usually accomplished by simply running the infer b function several hundred times, and then returning the index of the cache line that was the quickest to access, averaged across all of those iterations. Now, if you're interested, we actually have a full working example of this available on our GitHub page, linked both up on the screen and down below the video. Now, at time of writing, the example is written specifically for Apple Silicon Macs, but it should actually be trivially portable to other platforms and operating systems if you're so inclined. There are some notes in the README. Now, the demo lets you specify the value to place in memory, default value 42, and it also comes with 3 other tunable hash defines. Firstly, how far apart we want to space each cache line in memory to help suppress CPU prefetching, default value 16 kilobytes to match the macOS page size. Secondly, how many times we should repeat the experiment and probe each cache line in the array, default value 300 iterations. And finally, how many times we should retry if we infer value 0. And that last one is another trick for improving the signal-to-noise ratio, as CPUs tend to have an inherent bias towards using a placeholder value of 0 during speculation, depending on whether certain race conditions are met or not. Now, compiling the demo and running it on an M2 Max MacBook Pro, we see the value of the byte in memory has been correctly inferred as being 42. And this took about 1/10 of a second for us to infer using the default values for those tunables that we saw on the previous slide. And this is fairly reliable, so we can keep running this over and over and we'll keep seeing value 42. That said, there is still some noise every now and then, so here I ran it 1,000 times in a row, and there were 2 instances of the inferred value being wrong. So that's a greater than 99.8% accuracy for a read speed of around 10 bytes a second. But the whole point is that we can tweak those tunables to try and strike our desired balance between speed and accuracy. For example, here we've dropped the spacing between cache lines in our probe array from 16K down to 4K, and you can see this does run much faster now because we spend much less time flushing the array out of the data cache line by line. However, the accuracy also goes out the window. In fact, we've failed to correctly infer the value of the byte in memory a single time in these 10 runs here. So clearly, the CPU prefetcher is doing a very good job of pulling large parts of the probe array into the data cache here before being explicitly asked to do so by software. Now this time, we've bumped the spacing back up to 16K, And what we've done is dropped the iterations down from 300 to just 10. Now we're running an order of magnitude faster than on the previous slide, and our accuracy is looking much better. So we're correctly inferring value 42 most of the time. However, you'll notice that 2 of the wrongly inferred values are zeros here, and it's not a coincidence that those 2 runs also happened to take around 4 to 5 times longer to infer that value of 0 than the other run that incorrectly inferred value 225. So this is an example of the inherent bias towards value 0 that I mentioned a few slides ago. With that in mind, let's bump up the retries if 0 from 5 to 50. And that's looking much better now. So if we run this 100 times in a row, we're getting an accuracy of around 93% and a read speed of around 300 bytes a second. Doubling the iterations from 10 to 20 at this point, so keeping the spacing at 16K, keeping the retries if 0 bumped up from 5 to 50, well, now we're getting an accuracy of greater than 99% and a read speed of around 150 bytes a second. So yeah, if you're interested in how this kind of stuff works, feel free to go and download the demo code from the ArchAdept GitHub page and have a play at tweaking those tunables on your system. Okay, cool, Ash, but what's the point? After all, right from the beginning, we already had access to the byte in question, right? We can just directly dereference the pointer like readB does here, no problem. And yes, that's right. However, what we've just seen is that, in principle, the contents of memory may be inferred based on the presence of some other cache line being in the cache. And I want you to keep that point in mind while we explore this code a little bit further. So let's say we update our readB function to be like this. Rather than taking a regular address, we're now taking a pointer to some kernel address, dereferencing it and returning the loaded value. What's going to happen here? Well, clearly this isn't going to work, right? If we're some user space application trying to arbitrarily read some kernel space address that we don't have access to, then the MMU is going to raise a permission fault and our application is going to be killed. And of course, the exact same thing will happen if we try to dereference a kernel address in our infer-B function too, right? Yeah, of course it will. This is not a trick question. So we're fine, right? Well, I want you to consider what actually happens when the CPU comes across the load instruction that's reading from kernel space. You see, many CPUs have a load store pipeline optimization in which they perform the permission check and the actual load of the data in parallel. And this is supposed to be fine because from an architectural perspective, we'll still be verifying whether the permission checks all passed, and if not, we'll be raising an exception. And that exception typically causes all in-flight instructions to be abandoned. It synchronizes processor context up to the point of the faulting instruction. However, we've just spent quite a bit of time talking about how allocations into the cache may be used to infer the contents of memory that we don't have access to. And as you can see, there does exist a race condition here between the permission check being enforced and this load pulling the data into the CPU, with that data then being used for subsequent speculative loads from the probe array. Now, thankfully, that race condition is usually so small as to be basically impossible to exploit, because the permission check will be raised very quickly. However, we're actually missing an important detail from this flowchart here, and that's the fact that we can't actually raise an exception, nor commit the result of the load to architectural state until all prior instructions have themselves been architecturally resolved. And this makes sense, right? So we may have reordered this load before some earlier load, and then that earlier load ends up generating its own synchronous exception. In that case, this load will be one of those in-flight instructions that gets abandoned from the pipeline while the CPU synchronizes context. Similarly, we may have speculatively executed this load past a conditional branch that we didn't yet know was taken or not. So we can't raise a synchronous exception or commit the result of this load to architectural state until we know whether this load should have even been performed in the first place. And that represents our way in. You see, what we can do in our user space application is wrap our read of the kernel address in an if statement, which we know never evaluates to true, meaning we never architecturally execute the read from the kernel address. And yet, the CPU may speculatively execute past that conditional branch and perform both the read of the kernel address and the dependent read of the corresponding cache line from our probe array, all while waiting to see whether that if statement evaluates to true or not. Now, there is, of course, still a pretty tight race condition here between the CPU allocating one of the cache lines in our probe array into the cache and the CPU realizing that the if statement evaluates to false and that those two loads should never occur. However, there are a bunch of little tricks that we can use here to extend the window of that race condition. For example, we can try to ensure that the CPU misses in the TLB for its read of the never variable and then misses in the data cache for that variable too. Perhaps we even use the kernel's user space driver APIs to allocate the never variable in non-cacheable memory, ideally in a region of memory that we know is slower than regular DRAM to access, such as some SRAM or flash hanging off a downstream I/O bus. Meanwhile, we can also try to ensure that the CPU hits in the TLB for its read of the kernel address and its read from our probe array. Okay, so what does all this mean? Well, in case it hasn't quite hit you yet, it means this little bit of code you see right here is capable of arbitrarily reading out the contents of any kernel space address. I repeat, any kernel space address, without even needing to interact with the kernel. We can simply compile this code sequence, like this, into a malicious user space application, and then read out the entire contents of kernel space memory, if we so wish. And that's the Meltdown attack. Maybe you can see now why it was deemed to be so catastrophic a security vulnerability when it was first disclosed. It completely breaks down, or I guess you could say, melts down, the fundamental security mechanisms built into the CPU to prevent unprivileged software from reading memory that it should not have access to. Now, when it comes to defending against Meltdown, there are two criteria that must be met in order for a CPU to potentially be vulnerable. Firstly, the CPU must be able to perform two dependent loads under speculation. That's because we need to be able to perform both the speculative load from kernel space memory and also the dependent load from our probe array, where the address of that second load is determined by the result of the first load. In other words, there's an address dependency from the speculative load from kernel space memory to the speculative load from the probe array. And that usually rules out the smaller, more power efficiency focused cores. It's the bigger, more performance-oriented cores that have a sufficiently complex out-of-order pipeline and enough rename registers available to permit two or more dependent loads to be executed together under speculation. And by the way, this first criteria also applies to Spectre. However, for Meltdown to work, the CPU also needs to be able to defer enforcement of permission checks for speculative loads. For example, because the permission check happens in parallel to the load, and the result of that permission check is only used later to decide whether to raise an exception or to commit the result of the load to architectural state. That's actually quite rare for ARM-based CPUs. I'm not sure about other architecture licensee designs, but taking ARM's own Cortex-A, Cortex-X, and Neoverse designs as an example, only the Cortex-A75 ever did this, and they patched it out in revision 3. Now, when it comes to actually exploiting and defending against Meltdown, the particularly bad news is it's the easiest variant to exploit out of those that we're going to see in these two lessons. And that's because there's no need to find suitable so-called gadgets that we can exploit in the victim software, like an attacker would need to do for Spectre. More on that in the next lesson. However, the good news is that Meltdown is also the easiest variant to defend against, and ironically for the very same reason as above. So there's no need for us as the defender to identify exploitable in-kernel gadgets and to then insert the necessary barriers. We can simply make the kernel page tables private, and that completely prevents any Meltdown attacks like the one we just saw. To expand on what I mean by that, consider how the page tables work in traditional computer science. So typically, we'll have two separate address spaces, one for user space and one for kernel space, with user space typically being at the bottom of memory and kernel space then being at the top of memory. And that means any virtual address with upper bits all cleared to 0 is considered a user space address, and any virtual address with the upper bits all set to 1s is considered to be a kernel space address. I'm sure you've all seen kernel addresses being printed as FFFF something, right? Now in this model, we then have two separate sets of page tables, one that's used for translating user space addresses and another that's used for translating kernel addresses. On ARM-based systems, the user space tables are pointed to by the TTBR0 register, and the kernel space tables are pointed to by the TTBR1 register, TTBR being short for Translation Table Base Register. And of course, each entry in those two sets of tables then maps onto a single underlying physical address space. Now, here's the key point. Prior to Meltdown being disclosed, we'd typically have TTBR1 be pointing to the kernel space page tables, even when we were currently executing a user space application. And this made sense. After all, each entry in the TTBR1 page table would be mapped as privileged access only, so any attempt by a user space application to read or write that memory would trigger the MMU to raise a permission fault. But of course, we now know that this is not actually safe due to the effects of speculation. And so what we do nowadays is make the kernel space page tables private to the kernel. That is to say, we unmap the kernel space while executing in user space. The idea being that the CPU cannot speculatively read from kernel space while executing in user space if kernel space isn't even mapped, because only regions of memory that have been mapped as normal in the page tables can be accessed under speculation. Now, I guess I should clarify there, we don't actually fully unmap kernel space. Rather, what we do is make TTBR1 point to some dummy minimal set of page tables that give us just enough functionality to be able to swap over to using the proper kernel space page tables on kernel entry. We then do whatever work in the kernel is required of us before swapping back to the dummy page tables and dropping back into user space. Okay, so that was a brief introduction to speculative side channel attacks in the form of the original Meltdown attack. Join me in the next lesson then, where we'll build on this new understanding by exploring some other attacks, including Spectre variants 1 and 4, as well as straight-line speculation, and we'll also see some of the new barrier instructions that ARM added to the architecture in response to these attacks, and we'll learn how to use those new barriers to defend against them. I'll see you there. Thank you.